Boeing has always been part of my life. My dad works at Boeing. He's worked here for his entire career.
I'm a second-generation engineer.
Both of my kids fly Boeing platforms. One flies F-15s and the other one flies C-17s.
I'm a third-generation Boeing employee. My grandma and my mom both worked here.
I'm third-generation Boeing. My grandpa worked here, my mom, my dad, my uncle, my cousin, quite a few people in the family.
It takes a real team to make progress, but it has to be balanced with a culture that's respectful and with people that truly honour each other.
The culture has, I would say, ebbed and flowed, and there were times where it was really negative and really down, and quite honestly, the past few years, that's how it's been.
Boeing's culture today is changing. It's not there yet, but the culture is definitely on the rise.
I think we've got work, but I see the right trends to get the work done.
You see a lot of people that still have questions about where we're headed, and you see a lot of people that know where we're going and are really driving that change. And so we're a work in progress, but I'm so excited for where we're headed.
When I saw the new Boeing values and the behaviors, I was enlightened. Before, it just seemed to me like putting stuff out there on paper, right? These ones actually resonate with, I think, a lot more people, and myself included.
I see so many people with their values and behaviors printed out at their desk, and we speak about it not like this is Boeing's values and behaviors, but this is our values and behaviors. So I think it's just brought everybody together.
We need to see our leaders actually living and breathing these values, because if they are, then that is inspiring the next generation of people coming into Boeing. We don't want leaders that are just sat there being a bit stale and they're not kind of leading in the way that other inspiring leaders are.
Especially in the last year, we do see quite a bit of difference. There are a lot more interactions between the upper management of the company as well as the individuals within the organization.
The one thing I would offer to our leadership in this company is don't ever give up on this. It is a perishable thing. People need that motivation. People need that confidence that what they're doing is important.
Listen to your employees, the ones here on the ground floor, the ones building the product, the ones that are neck deep in all what goes in on these airplanes. They want to do a good job, and they have good ideas. They have great suggestions. They bring so much to the table.
The ability of our teams to look out for each other, to respect each other, to be courageous, those are the things that are going to help our culture turn the corner.
I think because we've been in such dark times, there is this lovely light that I can see in the future that's going to change things and just drive positivity within the teams as well. It's a great future ahead of us.
Good morning, good afternoon. I'm Jonathan Fulton, and I'm here today with Bryson White. We spend most of our time working in Boeing's manufacturing lines, using modeling and simulation, really focusing on how these systems actually behave, and quite frankly, not just how they're supposed to behave on paper. Today, we're going to walk through one specific problem space that comes up a lot in complex production environments, and that's really around how we represent and manage work as it moves through the system. So just a quick roadmap so you know where we're headed today. First, I'll ground us in the complexity of these production systems and, well, why a lot of traditional approaches tend to fall short. Then we'll level set on task sequences, just making sure everyone has a common mental model for how work is structured and how it flows through the system. From there, we'll walk through three approaches. The first, I'm calling the traditional method. The second, a hybrid approach. And then finally, a more flexible method that we found scales much better in real-world conditions and represents the complexities that we tend to see in everyday production. We'll show you the outputs, what you actually get from the model, and then close with where this becomes practical and valuable. We'll keep it moving, but the goal here isn't just to show models. It's really to show how this actually helps you make better decisions in messy, real systems. So let's start here. Because if you don't anchor on this, the rest of it isn't really going to land. Production systems, especially high complexity ones like in aerospace, they should come as no surprise, but they're not linear. They may look that way on a schedule, and on paper everything connects nicely. Task A feeds task B then feeds task C. You got clean handoffs and predictable timing. In reality, it behaves a lot more like a GPS. You don't just set the route once and follow it exactly. There's traffic, there's accidents, there's reroutes, and you got timing differences. And those things, they all compound. That's what's happening in these systems every single day. You got delays that compound quickly. A problem at one station can cascade downstream and create significant schedule disruption. We can't model everything as a simple bill of materials. The sheer volume of parts and the way they interact across assemblies, well, that makes the bill of material approaches not very scalable. Stringent traceability requirements mean that every single action on that airplane produces paperwork and adds steps that, well, quite frankly, they consume time and capacity and sometimes even be hidden. Tight tolerances increase the chance of rework. Rework not only eats time and resources, but it also introduces variability that ripples through the schedule. Let's think about customer variance as well, and low volume per each type of variant. The benefits of the traditional learning curve, well, we don't really get to take much advantage of them. As I mentioned, each airplane's interior could be completely different than the last. And the important part with all of these, they don't all act independently. They interact, and that's what makes it really tough to wrap your head around. Given these realities, spreadsheets and static analyses, well, they're often insufficient. And that's where simulation really comes in and shines. By building a realistic model of the production system, we can answer questions and test scenarios that traditional methods, they just really struggle to address. They assume if we optimize each position, the whole system will be optimized. And that may sound logical, but it breaks down pretty quickly. Because what actually drives performance is how that system absorbs variability, not how perfect each individual step is. So instead of thinking in terms of, did we finish everything in this position? We start thinking in terms of, is the system still flowing? And that's a big shift. This is where simulation really becomes necessary and not just helpful. Because now you can introduce real variability. You can start to see how those disruptions propagate. You can test different ways of absorbing that variability. And the real important part is it's not in isolation. It's across the entire system holistically. One of the key enablers here is what we call dynamic workflow. At a high level, it's simple. Instead of forcing all work to complete exactly where it was planned, you allow certain work, when it's safe and appropriate, to move forward with the product. That one change does a few important things. It prevents local delays from shutting down the entire line. It keeps overall flow moving through the system. And it gives you options to manage variability instead of just reacting to it. We've seen consistently that systems that allow for controlled flexibility, well, they outperform systems that try to enforce rigidity. Not because the plan was wrong, but because reality never matches the plan perfectly. All right, this is probably the most important concept in our whole discussion, so I'm going to slow down here for a minute and make sure we really ground it. Let's start with how these systems are supposed to work. In most production environments, especially flow-based systems, we're pulsing product through a series of positions. Each unit comes in with a defined statement of work. There's an allotted amount of time at that position, and the expectation is pretty straightforward. You show up, you complete the work, and when the clock hits tack time, you move. That's the plan. And if everything went exactly to this plan, well, it would actually be pretty easy to model. Every task finishes where it's supposed to, you got no carryover, no surprises. But unfortunately, that's just not how these systems behave. Because of all the things that I've already discussed, like variability, rework, those dependencies, you end up in situations all the time where work just doesn't finish in that position. And when that happens, the system doesn't stop. The work moves. Now this is where things start to get interesting, and honestly where most models lose the plot. Because that movement of work introduces a whole new layer of complexity. Some tasks can move forward with the product. Some physically can't. If you think about things like our joint or structural rigidity, some require specific skills that may or may not be available downstream. So now, instead of clean handoffs, you got work, people, and tools all interacting in ways that, well, they weren't originally planned to. And that's where you start to see people chasing the product. Tools becoming constraints in unexpected places, and small misses turn into system-wide delays. This is exactly the kind of behavior that's hard to capture with traditional approaches. So this is where task sequences start to come in, and specifically how we leverage them in Simio. At its core, Simio gives us a way to define a task sequence as a structured, ordered set of work steps, each with predecessor logic, resource requirements, cycle times, and execution rules. So instead of just moving entities from one server to the next, we're actually embedding the work itself onto the entity. And that's a big shift, because now the model isn't just tracking where the product is, it's tracking what work is completed, what work is remaining, and what constraints are tied to that work. That's what allows us to represent the system at a much more realistic level. Now, traditionally, even with task sequences, we tend to bind those tasks very tightly to positions, meaning this work happens here and it has to finish here. That works fine, well, until it doesn't. Because the moment something slips, and it will, you're left with two options. You either stop the system or you break the rules. And most real systems end up doing some version of the second one anyway. They just don't model it, and that's the gap. So what we're doing is taking that Simio task sequence capability and extending how we use it to enable dynamic workflow. Instead of forcing everything to complete exactly where it was planned, we allow tasks within the sequence to pause, transfer, and resume execution at downstream positions. Again, not randomly. This is governed by logic. Dependency checks, you got safety constraints, resource availability, so the integrity of the process is still maintained. But now the overall system has flexibility. And that changes behavior in a big way, because now you're not blocking the entire line for one incomplete task. You're not forcing inefficient workarounds that really nobody planned for. And you're not pretending the system behaves perfectly when it doesn't. Instead, you're modeling what actually happens. And more importantly, you can test it. You can ask, where does flexibility actually help? Where does it introduce risk? When does moving work improve flow? And when does it just push problems downstream? You also start to see trade-offs more clearly. There's always tension between local efficiency, finishing everything in position, and you think about it from that larger system performance perspective, keeping overall flow moving at the entire system level. Dynamic workflow, enabled through how we structure these task sequences, that lets you explore that balance. And one thing we've seen consistently is if you optimize purely for local completion, you often hurt the system. If you allow controlled flexibility and focus on flow, you can absorb variability much more effectively.
Before covering how we model a dynamic work movement, I want to jump into what we call the positional approach. The positional approach is a typical Simio model that has task sequences on the server itself. So you can see here that we have a source, position 1, position 2, position 3, and an exit. If you are familiar with how task sequences work, each one of these positions has a task sequence. In this model, 100% of the jobs in your task sequence has to be completed. In 99% of production systems, this is going to be good enough. Luckily enough for us at Boeing, this is not. This is ideal for identifying bottlenecks when trying to balance a line to see what servers are being blocked. And this also requires basic to intermediate Simio knowledge for straight line flows that we are using for our production system. Where it doesn't necessarily answer mail, it lacks the flexibility to handle constraints of late parts, certifications, whatever constraints are driving a delay from the nature of our production system. Not going to hold an airplane with thousands of jobs and millions of parts for a few decorative items. Lacks the ability to look at overflow parking type analysis for handling constraints of, like I just mentioned, late parts and certifications for finishing up last minute jobs that are held. How many of these spots are required based on the analysis? We're not able to do that in this approach. This drove us to innovate a different approach to model something that incorporated work movement between positions, which we call the hybrid approach now, since it's not our final product for solving this issue. But it's something in between the final product and our traditional approach. Now that we covered the positional approach, we can jump right into the hybrid approach. So you can see here, this model is structured very similarly to the one on the slide that we just covered. We have a source, we have a position 1, a position 2, a position 3, And then this is where it diverges from the positional approach. We have 3 overflow positions. How this works is very much structured like a typical task sequence in any other simulation model. We have a task table for position 1, task table for position 2, task table for position 3, and then we have task tables for all the overflow positions as well. Overflow 1, overflow 2, and overflow 3. Where it gets a little different from your typical task sequence tables, I think it would be best to just go to the data right here. It is structured a little differently to where position 1 has all positions 1 task. Position 2 has position 1 task and position 2 task. The reason behind this, you can see here that we have this complete column and this mid-process column. This is what is going to make the magic happen on this approach. This is where right when a job is completed, it's going to check it as complete. And this is what makes it possible to be tracking the jobs for whenever we move from one position to the other. All the data in position 1's task sequence get transferred to position 2's task sequence. From position 2 task sequence, and moves all the data to position 3. And this is what makes it possible for us to go and model dynamic work movement with work moving from position to position. The reason why this works is because once your part moves to position 2 and all that data moves from position 1 to position 2, it's going to do the full position 2 task sequence, which includes all position 1 jobs. And we have just a check as the start of your task to say, is this job complete or not? If it's not, then do the process. If it is, then skip it. So you're doing the full task sequence for all these positions. However, it's only going to work the ones not completed. So that's where we're able to go and model the work moving from position to position. And then the mid process, we kind of mentioned, if a job's in the middle of a process and it gets interrupted and then moved over, it's going to then track the remaining time remaining on that job and then complete that in the next position. So this is what makes it super dynamic and able to model the dynamic work movement. Some pros, we're able to have work move. We're able to see where headcount is required down the line once constraints open up. So if we have something that was supposed to be done in pause 1, if it's going to be open up and overflow, how does that headcount cycling look like? Do we need to have more heads? Do we just need to have a better cycling plan on that to not impact the position 1? Or how would we go about approaching that? The cons are this requires a task sequence and not just a normal task sequence. It is a little different to where if I have 50 servers and on server 1 of the 50, I have to update a task sequence change, I would have to go and scale that out to all 50. You can do Python scripts or automate that somehow. However, it is not a streamlined approach. This requires advanced Simio techniques common to custom tokens and custom states, which not many people are familiar with. Also, downfall, having to have predetermined routing logic to where you can't build in flexible routing without having a huge backend change, because each one of these servers, you have 4 different process logics, and you have to determine where it's going to go next for the table, and it's not flexible enough to go and have dynamic changes to your routing. And building off the backend of each server, there's a limit of overflow analysis you can have. You can't just have infinite overflow to see like how many would you need if you had no mitigations for overflow. Each one of those servers you have to copy paste and make a new one, which then involves changing a few things in the back end. So it's just not very scalable at its current state. This is why we went to go solve for a final solution that we believe is. Now that we covered the hybrid approach, we can get into why we're really here today. I'm excited to share with you the Model and See approach, a model and technique that offers a fresh perspective on how we handle task sequence and resource management in complex production systems. As you can see here, this looks very similar to the 2 models we have shown prior. We have the source right here, three servers, so position 1, position 2, position 3, and then common with the hybrid approach, we have this overflow position. Traditionally, many simulation models process task sequence at the server level, meaning the server dictates the order and flow of the task, and that's where it is housed. However, the model approach flips this concept by managing the task sequence at the part level. This means each part or entity carries its own sequence of tasks to be completed, while the server resources still perform the processing since they need it as a resource. This subtle but powerful shift allows for much greater flexibility and control over the workflow. And so to kind of expand within that, if you go to the model level with the data, this is where you would normally see your task sequences, and it's not there. And even if you click on your flow time, it's going to be our tag for this. This is because if you go to the model entity level, you're going to go to your data, and this is where you actually have your task sequence be done, and this is where it's going to be housed. If you run the model, you can see this task sequence on the airplane itself, or part, if it's a car, airplane, whatever you produce within your factory or operation. You can see each one of these houses a table, and this is being tracked individually by the aircraft. So you can see all the ones getting done for the complete or traveled, or I should say moved from position to position. So that is how is where it's being housed, and this is how it's structured. One standout benefit of this approach is the simplicity it brings to modeling maintenance. Instead of managing multiple tables or complex hybrid structures like we saw in the last model, to where you have to have all position 1 tasks in position 2 and all position 1 and 2 tasks in position 3, you maintain a single table or building or with one table that holds all the necessary information. This single table maintenance drastically reduces the overhead involved in updating or modifying the model, and in general, building the model at the very beginning. For example, if you need to change the routing structure of your model, you can do so quickly and with minimal backing changes. This is a significant improvement over the hybrid approach, which often requires a major overhaul of the model's logic and structure when routing changes are needed. The ability to rapidly adapt routing is crucial in dynamic production environments where processes and priorities can shift frequently. Another key of the model entity approach is that task sequence is being processed interdependent of position or location within the model. This means that the sequence of tasks a part follows does not have to be tied rigidly to a specific resource or station. However, the approach is flexible enough to incorporate process logic that references specific locations within the model if needed. This capability is particularly useful for scenarios involving tooling requirements, safety constraints, or other operational considerations where certain tasks must be performed at a designated position. This flexibility allows the model to be as rigid or adaptable as your system demands, providing a tailored fit for a wide range of production system environments. To expand on that a little bit more, this is basically saying if I have a task that's in pause 1, I would be starting that job in pause 1, but that necessarily doesn't have to be bound because the task sequence is not bound by position. However, you can build in logic to our process logic for the model entity that says in pause 1, I have this task that requires this one set of tooling that I cannot move to the second position. It's a fixed structure or what have you. It must be done in pause 1 or position 1. If that's the case, you would have to keep it in there, and it will keep that airplane in there until that job is completed, and then it would move to the second position. This is able to be built in even though it's being interdependent of the server. It can still reference where it's at within the space of the simulation to make sure it's doing its task sequence where it needs to based off resources required and the server location required. One major thing we had to go figure out was how to have the model entity level talk to the model level in far as resources. what we came up with the help of Simio and Hypercare was using relational tables to connect the model entity level tasks directly to the model level resource, creating a seamless integration that functions just like native Simio processes, but uses a different technique. This was one of the biggest hurdles, and thank you to Simio Hypercare for helping us out with that. This connection between entities and resources really make it to where we are able to scale this out for using this in our production system. And to elaborate more on that, I would go to show you in the model entity level. We have our data table right here with all our task sequence. There's no resources here. That is because we referenced the resources on the model level via this task table with the same exact order of the task sequence within the order ID or task ID. And this is a relational table to workers here. Now you're probably wondering, how do we even call that out, or how does that work? We would go to the model entity level and go to this process here, which is the actual task sequence process that is going to fire for each one of those rows. And you can see we have to execute here and execute there. So this first execute is to execute a process on the model level to seize resources. You have your delay for your flow time, and then you have your execute for the release. So this is how we're able to bridge the gap between the model entity level and the model level to be able to use resources just like native Simio can do in any other process, but using it within the model entity approach for this task sequence. Speaking of what I referenced to earlier on scalability, the hybrid approach was not very scalable at all due to the work that you have to do for multiple tables and having to have premeditated logic on where the airplane, or I should say part, needs to go next. The modeling approach offers several important advantages to that. It retains the benefit of the hybrid approach such as crew cycling and work movement, but it scales much better when dealing with larger models because you only need to maintain a single table. Adding new servers or resources is straightforward and does not require creating multiple process logics for each server. This reduces complexity and development time significantly. However, it's important to note that this approach requires an intermediate to advanced level Simio knowledge, particularly in working with the relational and foreign keys. This is a step up from the custom tokens used in the hybrid approach, however, but the investment in learning pays off in the form of more robust and flexibility. Another major advantage is infinite overflow capacity this approach provides. This is especially useful when analyzing scenarios such as determining the ideal number of parking spots for finished goods, managing waiting areas for delayed parts, or handling part storage. The ability to model these overflow areas without artificial constraints allows for more accurate and insightful analysis of system capacity and bottlenecks. So to expand a little bit more on that as well, you saw in the hybrid approach, we only had 3 spots for the overflow position. That would require a lot of backend building for different task sequences, different process logics. For this, you only have to change the initial capacity right here, and you can make as many as you want for just one position. So this is a huge improvement on the building of the model itself, to where it would take me 30 minutes to just build out a new server, maybe not that long, but get the idea of that. And then for this, it would take me probably half a second to type that from 1 to 2. So a huge improvement on the scalability of being able to look at our overflow position. One thing I did want to cover that Simio has a great feature that a lot of people, I assume, love, is the Gantt resource Gantts that is built into Simio. You would think with it being on the model entity, it might not be able to show you exactly what you're looking for on that Gantt. However, it is awesome that it does exactly what it would do on any other model, and it shows you the position based off the model entity for this we call airplane. So your position 1 and all the resources that are seized during the process and each task going on, even though it's on the model entity level, you still need that position to be used as a resource to seize it, to be able to do the task. So that's why it is able to be built in. Where the big value comes in is where you can see position 1, task 8. It spans across position 1 and position 2. This is when we're held for something, something's constraining it to where it needs to move to the next position. It can then go model that, and we can go put a resource plan together to go consume that work in the second position. If you scale this out to 100,000, maybe not 10,000 jobs, however, as many jobs as you can feed this does support within Simio. So we just picked a very simple example here to be able to do a proof of concept. Of course, no approach is without its challenges. The model entity approach is not a traditional way of modeling, so there is a learning curve involved. It may take some time to fully understand and implement the approach effectively. However, for a production system with complex constraints and dynamic requirements, the benefits far outweigh the initial effort. In summary, the model entity approach offers a scalable, maintainable, and highly flexible way to model complex systems at the part level. By leveraging Simio's relational tables, it connects tasks and resources effectively, enabling quick routing changes and robust resource management. This approach allows you to build models that are much easier to maintain, faster to adapt, and more reflective of real-world production dynamics. I think Fulton's going to touch more on the values and the why more than I.
So once you structure the model this way, with task sequences and dynamic workflow, the next question quickly becomes, well, what do you actually get out of it? And this is where Simio becomes really powerful, not just in building the model, but in how it exposes what's happening inside the system. One of the most useful views we leverage is the Gantt perspective. Now, Simio generates Gantt charts out of the box. That's not new. What's different is what's driving them. Because now, instead of just showing, well, the entity moved from here to there, the Gantt is reflecting the task sequence execution, where work paused, where it transferred, and where it resumed. So you're not just seeing movement, you're seeing how the work actually progressed through the system, and that's a big difference. And when you start looking at these timelines across runs, patterns can show up fast. You'll see things like the same task consistently slipping, work stacking up at certain positions, gaps where resources are waiting, or the opposite, resources constantly overloaded. And this is where constraint identification becomes very real, and it's not theoretical. It's not assumed, it's observable. So Simio makes it easy to pair that timeline with the standard output metrics that you'd see in pretty much any model, right? You got throughput, you got work in progress, utilization, delays, all that is still there. But now those metrics are tied to a model that actually reflects task level execution, resource interaction, and again, dynamic movement work. So when something looks off, you can trace it. Not just see that it happened, but more importantly, why. We also typically layer in dashboards on top of that. Again, leveraging standard Simio outputs. So you get these high-level system views of how well you're performing overall, and underneath of that, you get a detailed timeline view. Well, what is specifically driving that performance? And that combination is where the value really shows up. Because now you're not stuck in that loop of, well, we missed the plan, let's go figure out what happened. You can actually see where the system started to break down and ultimately what conditions led to it. And that is important because now you have a better idea of what levers you have to change in order to improve the system. Most importantly, none of this requires reinventing how outputs are delivered. Your standard tables, reports, KPIs, again, they're all still there. We're just enriching them by making sure that the underlying model reflects reality. That way our outputs don't just look right, they mean something. So I'll close it out here by tying this back to why this approach actually matters. Because at the end of the day, this isn't about modeling for the sake of modeling. It's about making better decisions in systems that don't behave cleanly. All right, so first let's talk about accuracy. When you combine Simio's ability to model variability, task sequences to represent real work, and dynamic workflow, all in conjuncture to capture how that work actually moves, you stop getting these utopian outputs, and you start getting results that reflect what really happens in the system. That's a big deal, because people make big decisions off of these numbers. And if the model was overly clean and simple, the decisions are also going to be really simple too. Second, let's think about people and skills. This shows up very clearly in this type of model, because now resources aren't just these generic capacity pools. They're tied to specific tasks with specific requirements and specific timing. And one thing becomes obvious pretty quickly. People aren't interchangeable, or at least not as interchangeable as some leadership often thinks. Simio lets us model that explicitly. Who can do what, where they're needed, and what happens when that alignment is off. So instead of just asking, do we have enough people? You can ask, do we have the right capability in the right place at the right time? Third, let's talk about bottlenecks and buffering strategies. This is where the combination of outputs and modeling really pays off, because now you can see which incomplete work actually impacts throughput and which doesn't. Not all delays matter equally. Some simply create noise, while others drive the entire system. And with this approach, leveraging Simio to run multiple scenarios, well, you can test where to place those buffers, how much flexibility to allow, and ultimately what business logic actually improves flow. Instead of guessing, you're experimenting now. All right, finally, let's talk about root cause. This is probably the biggest unlock, because now you can start answering questions like, what conditions consistently lead to missed work? What parts or processes drive the most disruption? Where does variability actually enter the system? And you're not answering that based on static data. You're answering it based on how the system behaves over time. That's a different level of insight. So what this looks like in practice is pretty straightforward. You build the model using task sequences and dynamic workflow in Simio. You run scenarios with real variability. You analyze outputs that reflect actual system behavior. And then you make decisions with a much higher level of confidence. At the end of the day, the goal isn't to make the model more complex. It's to make it more truthful. Because once that model behaves like the real system, now you can actually trust what it's telling you. I appreciate everybody's time, and I'm happy to get to any questions. Thank you.
Hey, good morning, guys.
Good morning. How are you doing?
Doing well. Good to see you. Really appreciated that, you didn't just show us where you landed in that presentation, but you walked us through how you got there through the different approaches. As modelers, we know there's always multiple ways to model the same system. So hearing how your team actually navigated that, I think, is something we can all learn from. So let's run through some questions. All right, first one here. For engineers ramping up, what helped shorten the learning curve? Is there anything looking back now that you wish you'd known on day one?
Yeah, so I think there's a couple things, right? In terms of the learning curve, there's plenty of opportunities to really leverage a lot of the framework that Simio and you all have already created in the form of SimBits, right? So I'll say we have definitely taken an approach, which is that we are not going to be the sole modelers, and these models, in order for them to be really successful and actually get used, we've got to bring everyone along on this journey, right? And so I'll say one of the areas that we're really trying to lean in on to ultimately shorten that learning curve is creating internal SimBits, right? So you guys have a plethora of useful modular pieces of logic that are absolutely critical to really learning Simio, but sometimes kind of lack the ability to resonate with some of the end users within the company, right? And so I think we've taken some of those methods and pieces of logic and really kind of expanded on that to resonate more with the larger community. And then ultimately put that in a place and make sure that it's known that those exist out there, to where if they have any sort of questions that pertain to a specific production system or a particular use case, that there's probably something out there to really kind of already leverage and help get them down that learning curve. In terms of things that I wish I knew on day one, I would say the big thing for me is that I wish I knew on day one was around tokens. And so I think tokens for me have always been a bit of they were sort of in a blind spot in which I said, well, I can do 90% of what I need to do without necessarily understanding the intricacies of tokens. However, I'll say that now that I have, ventured further into that realm, it has opened up a lot of doors for me to really kind of think a little bit more holistically, and putting together some models and frameworks that are much more scalable and much more flexible. Do you have anything to add to that?
No, I would just expand on the token piece is kind of the backbone of how Simio works in general. So like it's a very good thing to learn if you guys have not. So that's definitely a huge asset.
Yeah, it helps you get some of the fine grain control. So for new modelers out there, do your homework on tokens. And yeah, I loved your general comment that building your own repository of materials and your own center of excellence, that's something we've seen, really help with broader modeling groups. So that's great. Okay, next question. When there are multiple tasks that are ready to be executed, but limited resources, what, if any, prioritization methods does the model use to pick a task to perform?
So for the current model that we use for this example, it doesn't really have a priority on that, and that has been a challenge for us on bigger models as well. I can't remember, has Jacob been able to go do that on his mid-body model?
To a certain degree, yeah.
Yeah, so you are able to do a prioritization of which, if they're all, let's say, tied and ready to go, which ones are able to go be performed first. So that is possible within the prioritization.
Yeah, I think just to add on that as well, it's almost like from what perspective, right, are you trying to prioritize? And I think that's one of the major challenges that we've been really trying to shine a light on lately. When you think about the execution of our production systems, it relies on a number of different functions, right? When we think about quality and we think about structures and we think about the manufacturing teams themselves, everybody kind of has a different, I don't want to say different priority, we all have the same goal, but different functions can somewhat be measured differently, right? And so, for example, if you think about it from the lens of, let's say, a quality technician versus a mechanic who's actually performing that work, well, those quality technicians get moved around all over the place, right? And so sometimes they attempt to be more efficient and they'll go do batch calls, right? So we've got 5 different calls that we need to go inspect. Let's go knock them all out at once. And so their prioritization may be a little bit differently than we'll say the mechanic side of the house, right? And so I think the easy prioritization lever that we currently have in the model is really around from a resource structure. Do we work this and, do we stay in position and as that next airplane comes in and work this and then, have a secondary team or a secondary resource chase that airplane and that work that has traveled? Or is it my responsibility to ultimately follow with that work, close it out, and then come back into position? And so I think those are the sort of day-to-day questions that get brought up a lot. And again, it's a case-by-case basis, but the cool part about it is I think, from the Simio functionality and framework perspective, we have the ability to make that a lever. And that has now become one of those levers that we are starting to get a lot of our leadership to talk about and better understand, because that ultimately helps us drive better decisions and what those sort of run rules, or we'll say business logic, entail on a day-to-day basis. So yeah, there's multiple ways to say how are you going to actually prioritize, but I think it depends on what that resource's ultimate goal is in the long run.
Really good. Yeah, I think from a project strategy standpoint, it makes a lot of sense to start with your core functionality and then layer in the nice to haves as you go along. That sounds great. Let's see what we got next. How would you handle mixed model lines where different entities have different work content? Is that something you've run into here?
We have not necessarily went and gone and done that just because we have our one product, an aircraft. However, that should be totally possible to be done. You would just have to create a new model entity like you would have in your model table of contents at the very top right, and do the same exact functionality, just scaled across 2, just having 2 different task sequences attached to each one respectively, and then you should be able to scale that out for the model on your model that you're doing. So totally possible. I will say that we have not dabbled in that space yet, but definitely a possibility to go do that.
Yeah, I think just to elaborate on that a little bit, although it may not be a different airplane, like this completely different airplane to this completely different airplane, but we definitely have some level of, we'll say, configuration difference between them, right? If you think about, for example, the 787 airplane family, that consists of a couple of different minor models. Some of those can consist of, we'll say, different parts, and some of the different engineering and processes. But ultimately, a lot of that boils down to size, right? So if you think about the different derivatives, which is what it's called, inside of each one of those families, there's usually different seating configurations and different sizes, et cetera, depending on the requirements of that airplane. And so that is one area that I would say that we've been able to kind of dabble and get our feet wet to really understand what does it take to scale across a family of different parts, right? And so I think to get back to the original question here, there's definitely flexibility and scalability, and as Bryson described, to almost just have different entities, and then to his point, that would be a different task sequence stored on that entity, and then as you fire it into the line, you're just firing different entities rather than having to go and update a whole bunch of tables depending on what type of entity it is.
Very nice. Yeah, it seems like you have a good scaffolding in place there to sort of copy, or leverage the initial structure without too much difficulty there. All right. Let's see. Yeah, so are you fully converted? Do you use this approach for most of your models now, even if dynamic workflow isn't necessary? After this, do you find it more intuitive, or do you see yourself still using the more traditional approach with task sequences on servers in different cases?
Yeah, I would say one of the most important parts of simulation up there, as most important, would say how you go and attack the simulation, how you go approach it. I would jump right to the model entity approach if you're looking to model work that is leaking into another position or positions down the line based off your inputs given to the model and the impacts it has to the production system. However, if your jobs are completing in position, or even if you're studying a permanent like work transfer, if you want to move this job to position 2 permanently and studying that, I would still do the traditional approach with a task sequence, because simpler is just better in a lot of simulations. You don't want to overcomplicate it if you don't have to. So at the end of the day, I would say if your jobs are not fluid from position to position based off your inputs that you're giving, changing that output, I would just stick with a traditional model. It is not too hard to go transfer, but it does still take a little bit understanding of tokens to go do this. But I would say for the most part, if it's not required, we're not going to go force that down. So.
Yeah, and yeah, I'd say just to piggyback on that, you made the statement around the complexity factor, right? One thing that I'm really trying to hammer on folks on is this does not have, like, in order for a model to be useful, it does not have to be this huge complex model that has every intricate little detail in it, right? I think there's a clear strategy into developing a quote unquote successful model, but really it boils down to what questions you're trying to answer. And I would say kind of leaning on that right to left sort of methodology. Starting over here on the right, what are the specific questions of interest that we ultimately know today and think could pop up in the future? And that's going to kind of, working your way left. That'll lead you into, okay, well, what is the model architecture or infrastructure that's necessary to answer said questions, right? And so obviously when you think about travelers and dynamic workflow movement, the level of complexity in your model is going to significantly increase. But I don't think that that's necessarily a requirement for every single model, right? And I just want to be very clear that the more complex a model is doesn't necessarily mean that it's either more useful or more impactful. So we usually come into these with the mentality of starting simple and add complexity as necessary.
Yeah, fully agree that justifying a more complex approach or more scope within the model is the right way to go. Do that as needed. So that's great. All right. Yeah, folks would like to hear about the validation process. If you could share with us, what was perhaps difficult, or where were you successful in validating the model? So determining if it's accurate to reality.
Yeah. This is quite the fun topic, for sure. Because it's honestly one of the harder parts of building any model, at least in my mind. And so I'll say that there's no one size fits all in terms of validation methods. And unfortunately, our production system is no exception to the rule when it comes to current data collection, meaning a lot of the data that we had to validate against assumes a linear flow, right? It assumes that everything works as I described kind of in the presentation, right? Like in this very linear fashion, and there's clean handoffs, and that's just never the case. However, it's in a lot of instances, it's all we have, and it's the best we're going to get, right, for the time being, until we set up some better data collection systems. So that being said, I will say that there's a multitude of data points within our production systems that we have really tried to leverage and, for lack of a better term, Frankenstein together to ultimately understand, does this model reflect what we're seeing in production today? I would say that because we have sort of positional boundaries, some of those data collection methods kind of lend themselves to really helping us better understand how long we spent in a position. But that doesn't necessarily tell us, like from the statement of work perspective, what work was done. We just know it moved from one position to the next. So we definitely spend a lot of time, and I would say even from an engineering side of the house, we've identified a lot of opportunities just in the data collection system alone, and leveraging things like machine learning and obviously with AI coming online, what more can we get out of it? But I think this is one area where not just Boeing but the industry and all beyond really struggle in terms of how do we get better data collection systems to ultimately validate our models. And so, really long-winded answer to say that I think first and foremost, we leverage any of our real production systems that we can today to say, hey, does this match what we would see on the floor? We obviously have to be really strategic and smart around, what that sample size looks like. Is it how recent of a sample we're pulling from, et cetera, et cetera. But I think there's plenty of opportunity, especially when we think about conceptual designs and future airplane programs, to really kind of think about how do we create better workflows and tools in our current production systems to ultimately strengthen some of those bases of estimates and conceptual designs before we actually move forward, right? So I usually like to say grounded and demonstrated capability the best that we can, so that way we feel much more confident and our stakeholders feel much more confident in the decisions that are being made around the model.
Yeah, it's I think it's exciting when the modeling exercise can prompt you to go look further into data systems or collect additional data or sort of question, on the process side. And on this topic, I always think about the first V in V and V2, the verification. I mean, really using the tools in Simio to understand and have confidence in what the model is telling you. And I can tell from the presentation you guys did that using the Gantt charts, using the dashboards. So that sounds great. And I think we're gonna do one more question, guys, and then we're just about at time. So what do we have? How did you apply constraints to downstream positions to limit the number of worker resources being utilized simultaneously or the number of concurrent tasks running? We'll end with a nice complex question. But anything you could say to kind of the constraints from position to position, any challenges you face there?
Yeah. I'll say that it varies, right? But just to give a couple examples of, how that may vary. So long story short, when we create our schedules, those schedules actually end up driving the budgets, which means the number of available resources that we have actually in production is driven from our schedules. And so, to kind of tie a bow on that, I'll say that our schedules are very rigid, right? They're put together kind of with the mindset of, hey, we're going to have our resources available, we're going to have our parts available, and we're going to have our work available when we need it. Again, if you listen to any of that presentation, that's just not the reality of the situation. And so I would say that we run into a situation all the time where it's like we are not going to be able to pull a magic lever and get 100 more people, although that would be ideal. How do you work with what you got? And so I will say that we've utilized things like OpQuest to better understand what does that ideal allocation of resources look like across not only shifts, but maybe even positions. And it's down to a very granular level because, again, people aren't very interchangeable. You have some folks who are very skilled in a certain area or on a certain commodity. And you know, they're very critical to the overall success of the production system. So again, long-winded answer of being able to say that case by case basis, but I think our resources and our tooling are really our biggest sort of constraints that we tend to see from the downstream constraints, as well as I mentioned earlier, those levers that we go pull to say, hey, are we going to chase this lead airplane, or are we going to stay in position and work the next one and figure that out in the meantime, right? So tooling and resources are absolutely probably the most critical constraints that we see downstream, and in a lot of instances we don't have that flexibility. We're told, hey, this is what you get, work with what you've got.
Yep. The iterative process between insight from the model and what you can really, you know, where you really have play when you implement the real system.
Exactly.
We'll see if the control room serves up one more question. It looks like they will not. So I think we're at time, guys. Really appreciate your participation here. That was a great talk. It's good to see you.
You as well. Thanks, everybody.
Appreciate it.
All right.